Welcome everyone to our webinar here at the graduate program in mathematics of the University of Rio Grande do Sul. Professor Arthur Lopes is going to be the chair for today's session. So Arthur, please.
It's a pleasure to introduce Professor Rodrigo Bissacot, and he's going to talk about a natural compactification for a countable Markov shift and its thermodynamic formalism. Professor Rodrigo was a former student here on the bachelor and master program in mathematics in the University of Rio Grande do Sul, Porto Alegre. And it's a great pleasure to have you here. You have 1 hour at most, and it's now 2:15 p.m. Okay, thank you.
So, okay, thanks, Arthur. So it was thank you very much for the invitation, and Arthur, I think that Arthur suggested my name to Diego. It's as already was mentioned, I was a student here in Porto Alegre in the undergraduate studies and also in the master. And basically, what I will talk about is more or less some kind of corollary of my studies when I was at the UFRGS. Let's say 15 years ago. So I became a mathematical physicist after I went to Minas Gerais to do my PhD, and I always keep this my group here in São Paulo in this interface between regular theory and mathematical physics problem. So we are a group in mathematical physics, but with a strong let's say flavor in regular theory. More or less, you will realize more or less this during the talk. Well, this is let's say a very happy ending after 3 years of work. Most of the work that I will mention here was done inside of this project with Exel from Florianopolis, and where the students involved was Thiago, that is here with me. It was his PhD thesis, and also it was a master student, Rodrigo Frauzini, that now he's in Australia doing his PhD, and we worked in the last 3 years in this problem that it was let's say stuck more than 2 decades to try to do thermodynamic formalism for this compactification of countable Markov shift, which was an old object, but since there is some kind of technical barriers, it was, let's say, sleeping in the C star side until we arrived in this problem. So, since you told me that there is a seminar for graduate students, and I will try to go very slow in the beginning. You can stop me in any moment in ask questions. I will be very happy to answer here or also answer after the talk. So if you like more C-star algebra or groupoids on, let's say, more algebraic side of the theory, you can watch this Exel presentation in ICM that we were in the beginning when ICM happened here in Brazil, but we had let's say good enough results to present there. So in the talk of Rui, it was about this topic, but at this moment we have only constant potential. So now we have a complete theory. And in the end of the last year, Thiago finished his PhD thesis, and the thesis is on archive. You can read. The thesis is very big, but is because it's you have a lot of the details. So if you want to understand this, you can read the thesis. And the talk essentially is based on this let's say semi-final version of the paper. So I will discuss only a bit of what is we have done there, but I think that we will have at least a flavor what is happening in this topic now. So the idea, as Alvaro asked in the beginning, it's very basic, is the following. So you have the standard notion of what is a compact set, which means that if you have cover by open set, you always have a subcover that still covers a set. One important idea that you have to keep in mind here, that we will use this, let's say, philosophical idea to cover by finite number of sets. This we will be generalized in very, very general sense. In the end, that you can, maybe we will record in this first slide in the end. And if you will say that the space is locally compact, if you in each point you have a neighborhood that is a compact set. So this is very, very. If someone here does not know what is a topological space, you can think that is a metric space. So okay. So what is a compactification? That is the main the title of my talk. So if you have a space, the X, and you call a compactification of X, some space that is a compact space, the K. Which X has a topological copy inside of this space, which is dense there. So the bigger space is compact, and the original space is dense there, and the big spaces are compact sets. This is a general definition of a compactification. So a standard compactification, you have the line, the real line, and you just put a point at infinity, and you get the circle, the circle. And as Alvaro asked, so very basic stuff. So you have a topological space, and you have a contingent function. If the space is compact, the contingent function should be bounded. More or less every graduate student already know this, but despite of the fact that it is very basic, it will be crucial for us, and will be this more or less this last fact more or less allow us to do a lot of things that other groups were not able to do. So, okay, what is Markov sheet space? So you have an alphabet. For us, most of the time will be the natural numbers, or could be also a finite set. And you have, let's say, incidence matrix. So for us will be always transitive, that I will explain in a few minutes, but essentially is an infinite matrix. In each position you have 0, 1, and with this matrix you will codify your allowed words. Let's say you will be allowed or not if the enter of the matrix at this position is 1. If it's 0, you cannot pass from one symbol to another one. And okay, so after you have your matrix, you have all the sequence allowed by this matrix. So this is the Markov shift. So one very simple example, let's say take all the sequence of natural numbers. So the matrix, if everybody is 1. Okay. And the transitivity, that will be always a hypothesis for us, which means that you have two natural numbers, two ladders. You always can connect these natural numbers by the admissible word. So if you have, let's say, 3 and 4, you have some path that goes from 3 to 4, even that is not allowed go directly from 3 to 4. So this is a standard hypothesis in dynamical systems, and for us is very important for many reasons, and we always assume this. So okay, and now is as we still are in this let's say beginning of Alvaro, then this is the most, let's say, famous map in dynamical system is the shift map to just cut the first symbol. For us, the dynamics is always this. And another important set will be the cylinders, which are the sequences in your Markov shift, where you fix the first elements of your sequence, and the rest you are free. So one example is, for example, this. You have the sequence, or the first element is 2, and the second element is 1, and the rest you completely free. Of course, free, except to have to obey what your matrix said. Okay, And so examples, you have the full shift. Every word is allowed, complete all the sequence of natural numbers. And now appears one of the stars of this talk, that is the renewal shift. So the renewal shift, the allowed connections are in this graph with the arrows. So you can go 1 to 1 and 1 to any other natural number. And if you are in the position which is not the number 1, you have to go to the antecessor. So you have to go, if you are in the 4, you have to go to 3. You have 3, you have to go to 2, and there is no other options to go if you are if you are in the symbol that is not 1. The matrix is in the slide also, and this one will be one of the important examples in this talk. So now you see in my talk I discussed this kind of compactification. So one of the things that I will continues returning every time is about what is compact, what elements are compact, and etc. So if the matrix is whole finite, which means that in each line you have only a finite number of ones, we say that the matrix or the shift is whole finite. And if the matrix is whole finite, so the cylinders that I described in the beginning are compact sets. And this, for example, is an example. You see, pick some number. For example, 4. You are in the C. The only two possibilities if you are in the symbol 4 is you can go to 5 or you can go to 1. In just this. No, there is no other allowed path to go if you are in the symbol 4. So if you are in the sequence of natural numbers, if you are in the 1, you can go or 1 again, or you go to 2. So this is an example, or where you have a matrix with in each line you have an infinite matrix, but in each line you have only a finite number of ones. In this case, the cylinders are compact set, and this space is locally compact. This is a very important to keep in mind. What is here? You have a strong relation between properties in the matrix and in the space and the topology, etc. So here, more or less, is the summary of what happens here. So if you do have only a finite number of symbols, so your shift, this is the most studied case that your shift is compact. If the matrix is whole finite, so the shift is locally compact, but it's not compact, and is not whole finite, so it is not even locally compact. So it's the more general. The general case is the last one. So now we start to the things. So you see, it's a very natural strategy. You have we just saw in the beginning of the talks. Okay, if you are in compact space, so you can the continuous functions are bounded. You have a lot of properties that you can use. You have his representative theorem. You have a lot of things that you can do if the space is compact. So it's very natural strategy. Try to let's take a compactification of the space and study there and see what happens in the original one. So this was done 2 years ago by Ofer Schwartz, is a former student of Webinários, and he constructed what people call marching boundary of the space. You have extra points respect to the original countable Markov shift. But let's say you have a lot of restrictions respect to the general picture, because first the potential should has to be some kind of property that should be transient, and only works if the space is locally compact. So and he constructed, he obtained new measures with respect to what people had before, but you have to assume that the potential is transient, and you also have to assume that locally compact on your space. So what I will do now is the following. This compactification that I call it natural, I will try to convince you that is very natural, as I was convincing time ago. So I have to advertise that the difference that we did, what we did with respect to the Ofer or respect to Mike Todd and Godfrey Diom and these other groups, essentially always have some kind of extra structure to construct the compactification. And for us, let's say, I will present in a few minutes, but the compactification constructed by Rui Exel and Marcelo Laca is totally independent, only depends on the matrix. So it's natural in this sense. You have the matrix, you have the extra points. I will show to you. So a course of C-star algebra in one slide. So if you don't know what's the C-star algebra, you can find this very sympathetic, very friendly test of Rui Exel is in his home page. I don't know, 30 pages. You can learn enough to read papers. But essentially, a C-star algebra is a Banach algebra, which is a Banach space with respect to some norm. But you have also an evolution. You can think that in terms of is adjoint, for example, in the boundary operators in a Hilbert space. But the key properties is the first one is that makes the algebra Banach algebra. This in the first inequality, and it is identity that is, let's say, the key identity of C-star algebras. And okay, for us, let's say the important fact, maybe the most important fact, is this: that if you have a commutative C-star algebra, so you have only two options, or you are the space of continuous functions into the complex numbers. If you are a unital, if you have the identity in your algebra, or you are the space of functions, which is the case at 0 at infinity, when your algebra is not. This is this kind of let's say classification theorem you have in this more algebraic part of the theory. So there is no way to invent some new C-star algebra. That is, if you have a commutative C-star algebra, so you have certainly one of these two types. Okay. So and then in the 80s appears in the first time this very famous C-star algebra. There is a procedure to generate. If you have some collection of relations between elements, and you can construct the C-star algebra generated by these elements. So this became a very famous C-star algebra. That is the uniform C-star algebra generated by these partial geometries. Okay, I got look. You have these sums in this relation. So imagine that you have an infinite many partial geometries. What to do? You don't know. So it's a very non-trivial step. Start, let's say, to propose what is a Cuntz-Krieger C-star algebra when you have infinitely many partial geometries. It was a big problem in this area in the 80s after this paper. One thing that is very nice now, you start to see the connection between the algebraic setting and the topological setting. And for example, the algebra codifies the allowed words. For example, you take the partial isometries and take the product. It is not zero if only if the words are admissible. And here, if you take these projections, and you can show that these projections they commute each other, and you generate a commutative substar algebra of the original one. And as I told you, there is no escape. If you have a commutative C-star algebra, this is certainly a continuous the set of continuous functions of some space. And you see, you recover again the dynamics. You see the space which appears inside of where the functions are defined are exactly your space in the beginning. We are in the compact case here, right? So at this moment it was a big problem to try to do the analogous to the infinite number of projections. Let's say how to construct the Cuntz-Krieger algebra for infinitely many symbols. This was a big problem in this theory, and these two guys solved it. Okay, it took 20 years, as you can see, and Rui is one of collaborators with us, and Marcelo is one of is a new collaborator. The students are there doing sandwich programs and things like that. So they solve it, then propose some C-star algebra, which is the natural object as a Cuntz-Krieger for infinitely many partial isometries. And of course, what is the natural, or how you can prove that it's natural? You have to prove that if you have a finite number of partial isometries, you recover the Cuntz-Krieger algebra, the original one. So that's what what they did. So, and you see, it was some kind of running at this moment, and then before 2 years before this Kunjan, Pansky, Himborn, and Jean Renaud, they solved the locally compact case. So, and Marcelo and Rui, they gave the final answer. So, so I have to say that the object, this compactification that I presented here, it was not by us. It was on in this paper of Rui and Marcelo. But what happens is that the language that they use, using cross product and very, let's say, very C-star flavor, it is more or less, it was blocked for the people from dynamical systems. So until us. And just to mention what they did, they invented this relationship, which is which has you used your matrix to construct this, but as you see, is based on finite collections. Is a couple of finite subsets of natural numbers. You see, there is no series involved. There is some kind of you have some conditions over the finite sets, and you can recover the Cuntz-Krieger original algebra if you have a finite number of projections. So they constructed algebra. And as you more or less already should guess, what happens is exactly the same. If you have a finite number of partial isometries, you have the original algebra, and also for them, they codify the allowed words. Since the partial isometries, the product are 0 if only if the word is admissible. And now is the big step. When they did this, they constructed, again, the analogous commutative subalgebra as in the Cuntz-Krieger algebra. But what is the thing here? This space which appears here, it is always locally compact. And in general, as you saw in the beginning of my talk, the countable Markov shifts, they are not locally compact. So something which appears here certainly is not the usual countable Markov shift, but is something that you discovered now in this talk, which is in general is a compactification of the usual countable Markov shift. This is more or less the story of how this compactification was born, and so what appears inside because of the construction and by this is a very rigid theory. This C-star algebra, so is always locally compacted. So is something here which when the quantum Markov shift is not locally compact, certainly is not equal as happens in the compact case. So this is our what we call generalized quantum Markov shift. Is this space which appears here is always at least locally compact, and in the most important case is compact. So one thing that you can record in the beginning of my talk, you see the sigma A is always dense in XA. So since in most part of the case, in the important case, XA is compact, so XA is a compactification of sigma A by definition. And when you in the third line, when you have already a locally compact space, so these two sets are homeomorphic. So it's really a natural compactification. There is no extra term. There is no metric. There is no potential. There is nothing. There is only the matrix, and you get the space. So okay, So what? Okay, you have a natural compactification. So what you will do? You will do what you did before for the original space and compare the result. This is the most natural thing to do. So concretely, what is this space is the original space, the sigma A plus YA, which is a set of a special set of finite words. So the compactification essentially is the original space plus points which we identify with finite allowed words. This is the compactification that I will explain to you in the rest of the talk. So let's pick up an example. For example, the renewal shift. So the renewal shift is the graph of the allowed sequence is in the screen, and is compact. This compactification, the XA is compact, and you have only one infinitemeter, which means that the only symbol that you can go to infinitely other natural numbers is the number 1. This is the infinitemeter. So now I will describe to you how to construct these new points. The new points is exactly the points which the words with ending in an infinitemeter. So in this case, what happens that the only symbol which is an infinitemeter is 1. So this YA is the allowed words, is missing allowed here. So is the allowed words ending with the symbol 1 plus the empty word. I will discuss the empty word after. So this is the compactification concretely. So, but to work, you have to describe more. And of course, okay, but how? As I said, this space XA is always locally compact, but I want to know when is compact. So the easy way to see when is compact, and for example, if you look your matrix, if you have a row of 1s, is compact. And now I will do some kind of analogy with the beginning of the talk. Remember that we start the talk with saying that compact space are a space that you can cover always with a finite number of open sets if you have a covering. And now we will use this idea of cover something with a finite number, a finite collection of objects during the rest of the talk. So here's an example for example. So define the range of the symbol. So the range of the symbol is the elements where you are attained by, you have an arrow going from I to J. So the guys that where you can go from I to this symbol. So if we will say that the matrix or the shift, I don't know, is are compact if you have a finite number of symbols which cover the set of the natural numbers with the range of these symbols. And we can prove that the space that your new space, your generalized countable is compact if only if is are compact. So you see this kind of philosophy that you cover the objects by finite number of pieces of something is present here and will appear again after. One thing that why I'm doing this, okay? You use this strongly on the proofs. That's why I'm more or less highlighting this here. If you read the proofs, this is more or less of the key steps to prove that the pressures are equal and a lot of other things. So this is just a picture. So you see, you are covered by the range of I and the range of this finite or other number of natural numbers. So you cover all the natural numbers by this finite number of ranges. So okay, so now we start the let's say the discussion and okay, why there is some kind of let's say differences which are small, but people you see if you have a very established theory, in general, it's difficult to propose a completely new direction. So here is you have to prove that something that is very natural in some sense. So that was we did here. So you see, now we will start to discuss the thermodynamic formalism. So there you have a notion of pressure. The motivation is in physical mechanics, but let's keep the motivation and take a look at the objects. So you see, when the definition of partition function, we have periodic points, which is very important for dynamical systems. But I just told you that in the generalized setting, we have finite words. So a finite word is never a periodic point. So you see, if you follow directly the formalism proposed by Sarig, by Urbansky and others, you're not able to work let's say in the real sense in the new space, because you are looking only for infinite sequences. You never see a finite word. So we have to deal with this. So this is one of the things that is important to go to the conference. So I was in the conference with the students in the Rio de Janeiro, organized by Manuel Sadbauer. I don't remember if people from Rio Grande do Sul was there, but it was of this small conference of, I don't know, two or 3 days, I don't know. And I met Denker there, and we tried to explain for him what we are doing. And he said, okay, I don't know about groupoids, but take a look on this paper. So you see, there is a big change here when we describe the partition function and also the pressure. You see, you take pre-images. You go back. You take epsilons y this point y, which are when you apply the shift go to the x. It's completely different what you are doing. Oh, sorry. It's completely different what you are doing here, you see? So this is very good for us because you are going back, and going back you can do, even if you have finite word. So at this moment we discovered that, okay, let's pick up this formalism and forget about, at least for a moment, about Sarig and other people. Okay, so one problem that you do I just said, it is you have a very, very well-established formalism using Sarig tools, in what this school of Israel and Maud Urbansky and this guy is very well established. But actually this definition we just translate for this iterated function system. But at the end, let's say, just a spoiler, we are able to prove that these notions coincide in very general, let's say, the same generality where the formalism is developed. So actually, for us, they are the same. And one of the big results in the very end is that using the Denker-Urey pressure or Sarig pressure is the same for the same generality of the shifts and also in the potentials. So what means what? Means that we have a natural pressure even for the generalized setting, because if you restrict the potential, you recover everything that is done before. So this is one of the ways to prove that you are very natural. Is just take the restriction. What you get the same thing. So now a little bit more discuss about other proposals. You see, for us is interesting when you have a compactification which is different from the, let's say, the generalized space is different from the original one. So you have to, let's say, you have new things, you have extra points, let's say finite words, and the space of the non-empty words, let's say, where I can apply the shift at least a finite number of times, is an open set inside of this generalized quantum Markov shift, and the dynamics is always given by the shift map. The difference here is you cannot apply the shift forever. You can apply if you have an infinite sequence, okay, you can apply forever. But to have a finite word, you can apply only on a finite number of the times, which is exactly the length of the word. And the potential is defined only on this set of, let's say, shift table points, not in the in general. In the a lot of examples is the complete space except one point is the empty word. But sometimes you have more than one empty word. I will discuss after. So you see, the potential here, differently from the standard theory, is not defined for the entire space. So here start the people, let's say, I don't want to look this and this kind of reaction. People are very comfortable with the standard theory, so why do this, blah blah blah. So so why you have to convince the people. So let's do this. So one thing that you can use it. Let's say if you try to do in a different way, let's say, okay, let's take the compactification and let's try to define the potential in the entire space. Why you don't do this? Much more general, blah blah blah. Well, it's not like this because we have a lot of results in thermodynamic formalism for quantum Markov sheet, and we know, for example, when the pressure is finite. And the pressure is finite only if this series converges, is missing less than infinity. You have to ask the convergence of this series that in your right side. And what happens? So the potential should be to go to minus infinite. You see, it's not possible to be bundled in the full shift, for example. So if you want a regular potential which have a finite pressure, you cannot define, let's say, a continuous potential in the entire space because the space is compact, as I just told you in the beginning. So these people did this, and they have to consider only shifts with bounded potentials, with finite good efficient entropy, and etc. Actually, the contribution that what they did, they put a metric in the state space, in the natural numbers, which is bounded. So you use in each coordinate, you have a compact metric space. And so you have a compact space. And so which is a compactification on the original one, and they have extra points. But as you see, they cannot consider potentials if you are in the full shift, for example, which are unbounded. So your pressure explodes. So you have to take care on. You have to consider only shifts with a very small number of orbits. And another problem that happens that the extra point, the compactification, depends on the metric. So put different metrics, different space. So that's why I put in the title natural compactification, because the compactification that constructed by Marcelo and by Rui is totally natural in this sense. There is no extra to take the matrix, you have the compactification. So this is they studied, they have some results, but essentially, I think, I don't remember now, but even the paper, I think they mentioned that if you change the metric, you change the compactification. So let's discuss a bit how to construct more completely the space. So as I told you, the finite words, they are the words which are the end of these words are infinite meters. So this is just an example. You see, you want to construct the word omega. So you just take the sequence of elements which omega in something after. So you go omega for omega J1, from omega J2, etc. So you have a sequence of elements in your sigma A in the original space. But the space is compact, so it should be at least a subsequence which is convergence. For where? For the word omega. This is the standard procedure to produce the new points. And depends on the matrix, you have to completely control what is the new points. So, okay. So now I will try to describe how we work when, let's say, in the concrete terms, when you because I just said that this is a compact space. I didn't tell you how. Okay, but how you know that it's compact. And the thing is this: you will see the space XA inside of this compact space, which is 0, 1 to the free group of the natural numbers. So free group means you take all the products with the power 1 or -1, and you remove the redundancy, and you use this kind of strategy of that is very common in statistical mechanics, and to see that filled or not in each position of the free group. So it's a compact space because you take the product topology, and we realize the generalized quantum Markov inside of this space. The problem is to see how. So the first thing that that we should mention, that we will see this as a directed graph, and the label in the arrows will be the natural numbers, and exactly in the most natural way to see this. Everything that I'm telling you until now, except the part of the pressure and the incredulity, is inside of the paper of Rui and Marcelo already, but in some sense written in terms of more algebraic flavor, let's say. And inside of this space of 0, 1 to the free group, we will pick up this omega A space, which will be a compact set which satisfies four rules. First thing, that in the unity of the group is always filled. The configuration that we will consider is always connected. And if you have a word which is filled, and if you have this product, which is the word omega, so every subword of this omega is filled also. I will pick up a special set of configuration inside of this very big space to see the XA inside. This is the strategy. And the rule 3 is exactly this: how you use the matrix now to discover what is the right configurations. And so you see, if you have okay, what is our goal here? You have to identify some kind of space of paths. Finite path, which is the finite words, and infinite path, which will be the sequence of the original sigma A. This is the goal. So the first thing that you have to forbid is the following: you have to go to go further. You have to go to be able to decide where you are going. So it's not possible to go into the positive direction in two directions different. So if you have a position, you have only one positive direction, which is filled also. So in the left is not possible, but in the right is possible. In the most right picture, what happens is that, for example, you have a finite word. So it is the last filled element, and the rest is empty. And again, with this last rule, you discover how to fill the past. So you have, if you have two G and Gj filled, you use your matrix to decide if the past is filled or not. So basically, you discover what is the right configuration using your matrix. And as a consequence, this is proven in the paper of Rui and Marcelo. Only the filled points in this space have this form. So you have not this crazy, sometimes it's positive with exponent is positive, negative. No, just this form that are filled. The rest is empty. And now, more or less, let's say the concrete construction of the compactification. You just put the inclusion there of your sigma A, and this is the configuration there. You have this property that is the unique configuration in sigma in omega A, which every subword of X of this infinite sequence is filled. And now you take the closure. Remember, this is embedding inside of a compact space, and so this is housed, so the closure is also compact. Or let's say what happens sometimes that you have this. If you are not compact, let's say, okay, the construction that you have in the beginning is always compact. What happens that sometimes you have this extra point, which is the configuration only with the unity field, and you just take off and take the original space. So this is more or less the way that you construct the space, and how you realize now. Maybe is a good moment to see the pictures. So you see, here you have the unity, and here you have the finite word. So say you stop here, for example. So one thing, so let's say how to identify precisely the configurations and the finite words. So this is done using the notion that Marcelo and Rui also defined, which is the root of the configuration, which is exactly these blue arrows that you are seeing in the picture, which are the elements right before the last point filled in this some kind of positive finite path. So essentially, you have the last point which is filled in the after you pass the unity, and you have this the root, which is the symbol appears right before the last moment. So this gives you a bijection between the finite configuration and the finite words and the configurations in the space. So that's why we have complete control what are the objects in the space. So you see, so now what is the let's say the summary of everything. So pick the unity of the group. So we have two options, or you go forever and you in the positive side and you are in the infinite sequence as in the beginning, or at some moment you stop. So when you stop, you are now in a finite word, and you maybe you can how you can decide. So you identify the finite word because we know that there is a bijection between this finite word in the end plus if you consider the root, which is exactly the elements before the last filled element. So that's it. So the rest of the thing is just to work as in the original shift. For example, how to apply the shift. For example, here is a finite word. You see, is a word 3, 2, 1. So what does the shift do? The shift cut the 3. So let's cut. You see, to cut the 3 in the front of the finite word is just multiply everything by 3 power minus 1. So you get this word, the word 2, 1. So exactly as you imagine in the beginning, but you have to always think that you are in this, let's say, stem, which in this case is a finite stem, and you just act as the most natural way as possible. Okay, so let's discuss a little bit the empty configuration. So, okay, as I explained to you, let me see one thing. Let's return a bit. You see, this is the procedure to generate the finite words. So if you pick up, so you have to, let's say, to see finite words, you have to find the infinite emitters. So in the renewal shift, you remember the diagram of the graph. You have only one. Let's see. Okay, here. You see, you have only one infinite emitter, which is the symbol 1. So which means that the YA is exactly the allowed words with ends with 1. So this procedure is the concrete procedure to generate the YA space, the extra points. Okay, so how do you find your empty configuration? You find an empty configuration when you just start with something kind of let's say something that is running in the first coordinate, which is not, let's say 1, 2, 3, 4, 5, this will disappear. And because as you are in the compact space, and you have to go to somewhere. So you have everything that you have infinitely many possibilities. You disappear your symbol. So you disappear in the first coordinate. So you have the empty word. So in the graph, in the graphical representation, there is some kind of path of unity, and this exactly I'm showing to you. This is the empty configuration. I gave a talk in I don't know, in Mexico time ago, and people said, well, it seems very, very full of, is it not empty? Because you see that this is the main point here. The configuration in itself is after the unity. So you remember, you are inside of 0, 1 to the free group. So everything you have a lot of possibilities. So after the unity, there is nothing. But what is the symbol which allows to you infinitely many possibilities to continue? In the new shift, the only possibility is 1. That's why before the unity you have only this. And the rest of the picture that you are seeing, you just complete with the rules that I just explained to you before. So this is the empty configuration in the renewal shift. You can just say that is an empty configuration. That is, let's say, the empty word. But concretely in the graphical representation is this configuration. The rest that you not see here is empty, is not filled. And in a lot of spaces you have only one empty configurations. In another one you have more than one, and this will be very important to describe the conformal measures. So let's pick up one of the important measures in the in thermodynamic form. Let's pick the conformal following Denke-Urbanski. So this is the usual definition. You see what's the difference here? The difference here that the potential, so this function, the d, the density is defined only in the space of the points when you can apply the shift map. You see the dynamics also is partially defined, but this is the natural way to do things here. So this is the definition of conformal measure. So what you want to study? Okay, okay, you have new conformal measures. What is the connection of this conformal measure with the original one? And this kind of stuff. You have a new space, you have the control of the dynamics, you have to study the measures leaving different parts, the old one and the new one. And one key object is this YA family, which is get the empty state configuration, the empty word, and take the pre-measures. When you do this, is a partition for any, if you have more than one empty configuration, you will have more than one YA families. This will give you a partition of the finite of the points in the YA set. So this just example, just to keep very concrete. You see, this in the top is the empty configuration. So take the pre-measure. So you see in the second picture, you have exactly the configuration. If you act the shift map, let's say if you multiply by 1 to power minus 1, you get exactly the empty configuration, and you can continue doing this. Now in the second pre-measure, you have 2 possibilities and so on. So you see in each of them, you have this is the main stem. You see. And here is the unity. So you have this stem. The stem is to 1. This is the positive path. And here is another one, is 1, 1. You see? So you generate finite words, take the pre-measure of the empty configuration. And now, if you applied the equation of conformality to study the conformal measures there, you see for each empty configuration, the number of finite words are countable. So if you are a measure leaving this YN family, you just put a weight in each of these finite words, and you arrive in this equation. So this is the equation of conformal measure leaving on this new part of the space. So okay, but you can say, okay, but what is the connection between these new measures and the previous one? Exactly. The first thing that we have a control of the which are the extremal, which are the conformal measure living in each of these Y families, and this what we will prove. I just following the direction to there. We have many examples where these conformal measures, when you go to the right direction with respect to the beta, you converge to the original one. So it's some kind of the new space, the new conformal measures. These measures are seen; they are strongly connected to the original one because you can take the weak limits. We study also the weak converges of in this space, and you obtain the original conformal measure as in the Sarigi, Denker, Maldwin theory. So this was a more technical part, but we have a complete control of the weak convergence in this new space. The thing is that the base of the topology is more complicated, but in the end you can play more or less as before. So this is more or less the general theorem that we got in the examples. So you have some kind of critical beta. This critical beta in general is the Gurevich entropy of the shift. This was more or less natural because people in the quantum theory already arrived in the same critical point. For example, if you study KMS weights in C-star algebra, people know already that the Gurevich entropy is a critical point for the existence of these weights. So more or less, we obtain the same result for the classical part. And we can prove that these new measures, the weak limits gives to you the original conformal measure. So at this moment in ICM, we have more or less results only for constant potential equal 1. So Thiago is in the left, who is there. Elmer helped us a lot with this part of quantum Markov shifts. Frauzini is not there, and Fabrício is much bigger now. But so this is more in the middle of the 18, and we spent more or less in the last 2 years and a half tried to get more and more potentials. But just a few comments what we get at this moment. For example, take the potential equal 1, just constant. So you see in the left you have the standard theory, only 1 point, which is exactly the Gurevich entropy. And after us, you have a continuous after log 2. You have the existence of course, the measures are new. You see these measures they are living in this new part of the space. But if you take the weak limit, you get the original one. And you have some kind of modification. Let's say let's put two symbols which are infinitesimals. So you have a similar behavior. You have this. Again, you have the Gurevich entropy, which is the critical point. In the standard theory, you have only 1 point where you have the conformal measure, and after us, you have this cone. Actually, you can prove that the cone you have some kind of using the halves of this, and you can prove the entire cone converge to this collapse to this measure leaving the standard space. So it's very precise because, but this is natural if you look. Let's say if you look for the C-star algebra side, you more or less is not so surprised this thing. Okay, you have infinitely many also. Just modify the shift. Okay, and I should mention that if you want to see the results very in detail, let's say, as you see, Thiago was very happy when he finished his thesis, and all the examples he put all the details on the thesis. The thesis is very big, but because the details are there. So virtually he is in Poland, but he's not there yet. So he's here doing another paper. So okay, so just finish. We have the Ruel operator, but you have this kind of the potential is only defined in the let's say the shift table points, but the rest is analogous, and we can define the let's say eigenmeasure. again, you have this kind of asymmetry object because something is X, another is Y, but you have to do in this way. And we have the equivalence, but this is more or less well known in the standard case, and we prove it in the very general setting. We have a lot of other equivalents, but I just to pick up, let's say, to avoid too much technicality and definitions. And now is one of the nice things that we got. You see, this is a kind of a new type of phase transition, because we are able to prove that you always have an eigenmeasure for every beta, but the measure jumps from the original space to the new space. So because we glue all these results of Denker, Urey, and everything, and we are able to apply in this general space, and we can see that the measures before us, the measure just stopped to existing, just does not exist anymore, and after us it continues to exist, but leaving another space. So this is just a picture to compare the formalism, what you have before and after. Since we know that the pressure in this case is 0, so you get KMS state. So this is analogous to the Gibbs state, but in the quantum setting, let's say. And I will stop in a bit, and just to mention, let's say, the last notion of compactness. And during this investigation, we tried very strongly in the end now to prove the quality of the expressions of Denker and Sarigi, yeah, and Gurevich, which is used in general by Sarigi, and we succeed, but we have to put some hypotheses in the shift, and this is the hypothesis. I'm calling in the X compactness because, again, you see, now any of these roots, remember these blue arrows before the last point, which is filled, we call root. This area, this R, beautiful R here, is the root of something that empty configuration. So if you are able to find a finite collection of natural numbers with the source of these numbers covers the root, so you have this property that we call S compactness. And one way to see if the matrix is F compact or not is you have to see if the matrix has a column of ones. So you see, by original compactness, a line of a row of ones. By this notion of compactness, a column of ones. But again, this philosophy of try to find the right objects to cover what you are interested in is present in every argument. It's the same. But you see, there is no metric, there is nothing. It's just matrix and some kind of ideas. And okay, I will skip this, but just to present, let's say, the last result that we made a big effort to see this, to obtain this, exactly this. With the right regularity, you can prove that the pressure used by Denker and Urey, that you're going back, coincides with the pressure of Gurevich, which is used by Sarigi and other people. So this is the right pressure because, let's say, you recover the original pressure that people are using in the standard theory. So I think that after I have some results of existence and so on, but maybe the main one of the main last thing that we got, and we were very happy that we finally, when we put in the same level of regularity of the potential and the shifts, the result of Sarigi and what we got here. Well, one thing that, okay, but someone can say, okay, but this is S compact. No, yes, you're right, but look, most of the most important example satisfies this hypothesis. So it is very general in this sense. So, okay, I think that I will stop here, and if someone has to add something.
Thanks there. questions, please?
I cannot see nothing.
There is
Maybe
a
you can see.
I have a question. When you solve the problem with the Wheel operator, right, and find the eigenfunction and the probability, after that, it's possible to get some variational principal pressure that you have supremum of entropy plus integral potential. What will be the entropy of this new setting?
Yes.
It's a general question.
No, I got. I know that I think even with Alexandre, they have a paper with partial something to the entropy. And at some moment, we also think, okay, maybe to take a look there, but we stop a bit, okay, but who is over there? So you see, okay, what happens is the following. The entropy that I just mentioned here is the original one, because the pressure that I mentioned here is the original one. So there is no new entropy, there is no, let's say, new pressure, because all the effort that we did is actually to prove that if this pressure, let's say, that we got here, when you take the restriction, is the original one. So what happens that by the right hypothesis that we put, we are able to pick up even finite words and take back, not go further, but take the pre-images, using the Denker-Urey ideas, and prove that even for the finite words, when you take the pre-images, you got also the original pressure. So let's say I never look for invariant measures in the big space, because even the dynamics is partially defined. So maybe people that work in these partial defined things, maybe they have some natural, let's say, objects, and say, okay, maybe this is entropy, blah, blah, blah. But what happens here is the following. What is the entropy here? Is the entropy of Gurevich. Why? Because we prove that for this class of shifts, we get this equality between Denker and Urey and the Sarigi pressure. So the entropy for me, at least at this moment, is just the pressure of the zero potential. So see, but there is no, I understood your question. Let's say, let's try to prove the variation operation as in the standard one. For me, at least, because everything is very new, I don't see how to give to you a good, let's say, statement of the theorem, because the dynamics is partially defined. So it's difficult to discuss about the invariant measures and things like that. Everything have some kind of asymmetry. Okay, what I can say is the following. If you look in the paper, in the very end, we are able to get some examples in the full shift, because when Thiago defended his thesis, we have a lot of examples with finite entropy. So after we worked, and now we have a couple of examples in the full shift, but using the new shift yet. So what we get in the last week, but I didn't put in the talk because we are checking. We are able to work now in more concrete example in the full shift with more concrete examples where we have measures leaving the two parts of the space. Because you see, everything that I told to you, you are jumping. Or you live in the new space, or you are living the, you see, you never saw a real, let's say, what is a generalized conformal measure? You see, you don't see it, because everything that I just told you, you are jumping, or you are in the new space, or you are in the previous space. Now we get explicitly examples where we have measures with giving mass for the both part of the space. So it's maybe we'll get some new directions to more interesting things.
Another question, that potential that you mentioned, log n minus log n plus 1.
Yes. Oops.
This
yes.
Looks a little bit like Hofbauer, I don't know.
Yes, we took a look a bit in the Hofbauer, tried to get inspiration, but one thing that you are right, because you see, after a point you get zero pressure. You see, that's why we have the Kaiman states. So you have the pressure that is not trivial. At some moment the pressure is 0 and 0 after that. So yes, it's some kind of there is some kind of flavor, but we are okay. Now we have more interest in potential, but we are checking the calculations. So I decided to not say nothing here until.
Yeah, in the Hofbauer we have probability after the transition, but no KMS states.
I don't remember exactly now, but yes. But here we have KMSs for sure. Yes.
After
critical beta, we have KMS states for sure. We have KMS states, but they are living in the. Okay, Arthur. Since you know Thompson papers, Thompson called these measures because Thompson he didn't study Exel Laca algebra, but he studied graph algebras, which they have the intersections, but it's not equal. One of our results exactly shows that we have different main objects here, but in any case, Thompson called these measures as boundary measures, and boundary measure for him is the measure which are living in the finite paths. So for us, this red part that you are seeing, they are KMS states, but the mass of the measure is in the finite words. This is the situation.
Is the outside the set in the compactification. The part is not in the set.
Yes, exactly. You have the white part is the standard formalism, is living the sigma A, and the red part is living in the compactification. Exactly.
Okay. More questions, please.
Rodrigo, do you mind explaining again a little bit how you see your space in this 0, 1 to the power?
Yes. You know? Oh yes, Diego.
I got quite confused.
Yes. I have to confess to you, when we start to do this presentation, Thiago the position after one presentation in Poland, but we thought that people will understand very fast, looking for the pictures. But after a couple of talks, we discovered that we were completely failure in this, and I'm removing some of the. Yes. Unfortunately, the real life is more difficult than where you before. Oh, look, Diego. The main point is here. That's I think maybe is here. You see my mouse or not? You see?
Yeah, we can see.
Oh, you see the point is here, Diego. When you inside of 0, 1 to the free group, the free group always have the unity. Okay, so is here. So what we do is the following. Every point of the space is let's pick up a not empty configuration, a non-empty word, let's say. So you have something in the positive part. So, or you see this infinite path, which correspond a sequence in the sigma A, or you see something like this 3, 2, 1. You see, this is some kind of I cannot write here, but let's say pick up the following sequence. The sequence is the following: 3, 2, 1, n. On n is a natural number. So you see, you have constructed a lot of this sequence in your shift. So after the 1, you have something that is go to infinity. So the philosophy that this sequence of elements of sigma A, since the space is compact, you are going to some point. But which point? The point where this coordinate, which is going to infinity, it disappears. So you get the finite word. This is the philosophy to guess what is the right words. But so this is the element. This positive part we call stem. Now the stem is the last point which is filled, is the mainstay of this configuration. So we realize the finite words of XA here. After unity of the group, you take the main stem in the positive direction. So or you get an infinite path, so you are in the element of the sigma A, or you stop in some moment. So if you stop, you are in YA. If you're continuous forever in the positive direction, you are in sigma A. It's just this. The problem is that when you see this space 0, 1 to the free group is a giant space. So you have to identify the sigma A and the YA, you have to look for the specific part of the space, which are this positive path after unity. So if you stop, if there is nothing filling after this, so you are in the word in the YA. If you continue forever, you are in sigma A. Just this.
Nice. Yeah, thanks. I think I got a little bit better. Yeah.
Yes, I think that I think that the easiest way is to think in terms of past and future, and you think in terms of finite paths or infinite paths, and your present is in the unity of the group, and just go in the positive direction. If you stop, you are in YA. If you continue forever, you are in a point of sigma A. And to discover which are the points which are filled or not, use the rules. This is the important. But so in the beginning, I gave talks, and also Thiago spent a lot of time looking for these pictures, but we discovered that people don't understand even with a lot of. So we just changed the. You see, because this is the main stem. This is the point in the YA. Because in the renewal shift after 1, you have infinitely many possibilities. So you can stop here, exactly. You see?
Okay, thank you. Let's thanks Rodrigo again.